Hello, my name is Magnus Petersen. This is my tutorial number 13 on TensorFlow, and this is about visual analysis. You may remember in some of the previous tutorials where we plotted the convolutional filter weights, and it looked something like this. So each one of these squares is a 5x5 convolutional filter where the red pixels are positive values and the blue pixels are negative values. And we would then slide these filters across the input image and calculate dot products. This was described in tutorial number 2. The problem is that we can't really see what the convolutional filters are trying to recognize in the input image. So we need another technique for doing that. The basic way of visualizing what happens inside a neural network is shown in this flowchart here. So we start with an image full of random noise and we send it through our neural network. And then at some point where we want to visualize what is happening, we calculate the gradient of a feature or a neuron inside the network with regard to the input image. And then we update the image so that the feature is increased. And we do this many times. And eventually the input image becomes something like this perhaps, which means that this particular neuron or feature likes to see images that look like this. And we're using the Inception version 3 model here, which is very complicated. So it has many layers and each of them have many features. And we will see below how the patterns that the neurons like to see are fairly simple in the beginning of the network and then become gradually more complicated and abstract towards the end. We will use the names of the convolutional layers in order to identify them and instruct the system what it is that we want to optimize. And we have this helper function here for getting the list of the names for the convolutional layers. And when we execute it, we see that there are 94 different convolutional layers. And these are the names of the first 5, and these are the names of the last 5. If we go back to the flowchart, we see that the Inception model has a very complicated structure. So all of these elements in here are actually convolutional layers and they are working in parallel. And then the results are joined together or concatenated. And then we make parallel computations using convolutional filters again. And this continues, but we just choose to call it layers because it's easier, even though it's a complicated layer structure. So here we have the helper function for finding the input image that causes a neuron or a feature in a given convolutional layer to be maximized. So it takes as input an integer for the convolutional layer. This is just a number between 0 and 94. And then it takes a feature number, and we will see below what this means, but it just identifies the feature in that convolutional layer. And then we have the number of iterations that we want to perform and whether or not we want to show the progress during the optimization. So first we have to load the Inception model, and we do this for each time we call this function because we will add a lot of elements to the graph. And if we do this again and again each time we call the function, then we will run out of memory on the computer and it will crash. So that is why we create a new Inception model every time we call this function. And then we need a reference to the input to the Inception model, and this is the raw input image. And then we need a reference to the output for the predicted classes. So if we go back and look at the flowchart again, we have the resized image, which is tensor for the raw input image here. And then we have ypred, which is the output of the softmax classifier here. So now we have to create the loss function that we want to maximize. And the loss function is perhaps a bit of a confusing name, but it's very common to call it the loss function, so we'll just do that as well. And if we want to maximize a feature on the very last layer of the network, then this is what we're going to do. And we need what we call the unscale logits for the softmax classifier. And then we basically just take the scalar value indexed by this feature number here. If instead we want to maximize a feature of a convolutional layer inside the neural network, then we have to do the following. First, we have to get the name of the convolutional layer. Then we have to get a reference to the tensor that is output by the convolutional layer. And we do it like this. And then we have to create the loss function, which we do like this. The output of a convolutional layer is a 4-dimensional tensor or 4-dimensional array. And the first index is for the image number, and we only use one image, so this is not really used. And the second one is, as I recall, for the height of the image. and the third one is for the width, and the last one is for the output channel. So what we're going to do is we're going to calculate the loss function as the average over the output of the convolutional layer for the channel with this index here, the feature number. And I encourage you to try and modify this formula here. For example, put in a 0 here and a 0 here maybe, or something else, and see what happens when you optimize images using another formula. And then we get the gradient for the loss function with regard to the resized image. So this tells us how much we need to change each pixel in the resized image or the input image for the Inception model in order to increase the loss function. And this is just one line of code, but what is actually happening behind the scenes is that TensorFlow goes through the entire computational graph and calculates the gradient using the so-called chain rule of differentiation. And if we do this a lot of times, it adds a lot of computational nodes to the graph for the Inception model, and that is why we will run out of memory if we just build on the same graph again and again and again. So that's why we create a new Inception model every time we run this function. And then we need a TensorFlow session so we can run the graph. And here we initialize the input image with random values between 128 and 129. And this is about the middle of the color range for the image. So just a little random noise to get started. And then we want to perform a number of optimization iterations to find the image that maximizes the loss function. So we create a feed dict as usual, where we feed the image that we want to optimize as the input to the Inception model. And then we execute the computational graph, and we want to get the predicted class scores and the gradient and the loss value. We then calculate the step size using this heuristic formula here, which ensures that we make significant changes to the input image in each iteration. And then we scale the gradient using this step size, and we add it to the input image. And then we clip all the pixel values so they are between 0 and 255, so it is a valid image. And if we want to show the progress, then we print a bunch of statistics here. Finally, when we are done, we close the TensorFlow session inside the model object, and then we return the image that we have optimized. So before we see the results, we just need a few more helper functions. So we have to normalize the image so it can be plotted. And then we have a function for plotting a single image. And then we have a function for plotting multiple images in a grid. And then we have a helper function that combines the above functions. So it would run the optimization function 6 times, and then it plots the resulting images. So let's look at some results. At first, we just optimize a single image, and we do it for the convolutional layer with the ID number 5, and we want feature number 2, and we use 30 iterations, and we want to show the progress. So after the first iteration, the Inception model has predicted that our input image shows a dishwasher, but it's a very low score. And here we have some statistics about the gradient and the step size, and we have the loss number. And what we want to see is that as we perform more iterations, the loss number should increase. So let's see if that happens. So this is after iteration number 9, and now the loss value is higher than 12, and it started below 5. So it seems to be going in the right direction. And the Inception model is predicting that the input image shows a syringe with a score of about 15%. And when we have executed 30 iterations, the loss is almost 18. And the Inception model predicts that our input image now shows a BIP, but the score is very low, it's below 17%. And this is a resulting image that we have optimized. So it has these kind of slightly wavy, squarey patterns. And if we go back to the flowchart, we can see that what we have found is an image here, so that the 5th convolutional layer, and I guess it must be 1, 2, 3, 4, 5, this convolutional layer here, and it is the second output channel of that convolutional layer that reacts very strongly to the input image that we have optimized and shown below. So this image here causes the given output channel for the given convolutional layer to be maximized. So that is what that particular channel in the convolutional layer sort of likes to see in the input image. So let's try and optimize multiple images for each of the convolutional layers. And we start at the beginning of the network. And what we see is that the different channels in the first convolutional layer apparently likes to see different colors. And it's not solid colors, it's like there's a slight texture to it, but this one is green and this is gray and this is, I don't know the name of this color, some kind of green and purple and so on. So now let's do it again for the fourth convolutional layer. The index starts at 0, so this is 3, so that means it's the fourth convolutional layer. And here we see that the patterns become more complex. So the fourth convolutional layer likes to see patterns like this. And we can do it again for the fifth convolutional layer. And it seems that this convolutional layer likes to see sort of wavy lines, but they're going in different directions and they look slightly different. And here we have for the sixth convolutional layer, where the patterns are getting even more complex. So these are sort of square things, and these have ripples going in both directions, and these are weird shapes and other weird shapes. So as we get deeper, the convolutional layers like to see more complicated patterns. And here we have for the next convolutional layer, number 7, and the patterns get slightly more complicated. And for the next convolutional layer, these look almost organic, like the texture you might see in some kind of organic material. And then we have the next convolutional layer again, and these are more abstract. And if we go back to the flowchart, I think that what we might be seeing are some of the convolutional layers that are running in parallel inside this part of the graph here. And here's another example. And now let's jump up to layer number 21. And we see that the patterns get more complicated. There are more fine details here. And if we jump to convolutional layer number 31, it's even more complicated with more patterns inside patterns and so on. We can't really recognize anything in these patterns. It's just abstract, complicated patterns. And if we jump another 10 convolutional layers, the patterns look like this. And if we jump another 10 convolutional layers, the patterns look like this. And I should say that these are actually zoomed images. These are 100 by 100 pixels, whereas the full patterns are actually 299 by 299 pixels. And we will see an example of a full pattern below. So here is convolutional layer number 61, and it starts to become quite messy, and we can't really see what it is recognizing anymore. Just some abstract, complicated mess. And if we jump another 10 convolutional layers, this is what we get. And this is what we get for convolutional layer number 81. And this is for layer number 91. And here this seems to be becoming a bit more structure again, as the lines get more defined, but it's still just an abstract, chaotic mess. And here we have it for the very last convolutional layer, and it looks pretty much the same. So let's see what the images will look like for the final fully connected layer right before the softmax classifier. So these should correspond to classes of the output. So this could be monkey, fox, car, sunglasses, and things like that. But if we maximize the features of this last layer of the Inception model, what we get are, again, complex abstract images. There's nothing that we can recognize in these images. And we can try and let the optimization run for 100 iterations instead of just 30. And we wanted to maximize the feature for the kid fox. This is a kind of strange fox with big ears. And we can get the classification score of the Inception model to be 100% with this image that we are optimizing. And the loss becomes very big at 75. So this should be a very good match for what this neuron or feature likes to see in the input image. And we would expect or hope that it would show an image of a fox. So let's have a look. It doesn't. It just shows the same abstract, chaotic lines as before. And we can't recognize anything in this image. So what we have seen is that in the early layers of the neural network, the neurons like to see particular kinds of patterns in the input image. And as we get deeper and deeper in the neural network, it becomes increasingly unclear what it is that the network likes to see. And all the way towards the end, we would have hoped that our optimization procedure would find images that looked like, for example, a fox or a lion or a cat or a car or whatever, but it doesn't. It just finds a very complicated pattern that the network likes to see. You may remember from the previous tutorial, number 11, that we can easily fool the Inception model into classifying any image as any target class that we like, simply by adding some specialized adversarial noise. So what is happening is that the neurons or the features inside the network react strongly to probably infinitely many images, and only a small number of those images are recognizable to the human eye. And there are many proposals in the research literature for guiding the optimization process so it finds image patterns that are more recognizable to humans. For example, this paper here, Understanding Neural Networks Through Deep Visualization by Yusinski and others. And it proposes a combination of heuristic methods that, when used in combination and when the parameters are finely tuned, generates images that we can sort of recognize. For example, this is for the final layer, and these are images that maximize the neuron for the flamingo class. And we can sort of see these pink birds, which are supposedly flamingos. And here's for a pelican. And we can also see the pelicans here, and hartebeest. And here we have the class for black swan. And we can also sort of see that. But these images here show what happens if we choose different parameters for the heuristics. Then the images are not as clear. And I have given a link to the source code, which I believe implements these heuristic functions. And it looks like this. And I have tried implementing these myself, but I could not get it working. I could not optimize images for the Inception model that looked anything like this. It was just the same abstract patterns that we saw before. So I'm thinking that maybe the heuristics in this paper don't work for the Inception model, or I somehow misunderstood them and implemented them wrong. But I encourage you to try and modify the source code and see if you can get it working. And there's another paper here, which is called Multifaceted Feature Visualization and so on. And it's by some of the same people that wrote the previous paper. And this is much better at generating images that humans can recognize and identify. So here we have a bell pepper, we have an orange and a strawberry and pineapple. So how did they do it? The answer is they cheated. They took all the images from the training set, for example ImageNet, and they saw which ones maximize the given neuron or feature in the neural network. And then they clustered those images and averaged the images that were most alike. And then they used that as a starting point for the optimization. So the optimization didn't really find these images. They started with images that looked sort of like this. So I would encourage you to try some of these exercises and maybe see if you can find a method that makes the images more recognizable by humans. And I'd love to hear how you did it. And you can download this source code by clicking on the link below the video.